So, it is my pleasure to announce now the next speaker. So this is going to be Katharina Kohls, and she's a professor at the University of Bochum, and she is also head of the chair for system security group. And so the work of her group focuses on security and privacy of mobile network infrastructures. And before leading this group, she was also an assistant professor at Radboud University. And before that, she was also a postdoc at Bochum University. And so, yes, today, Katharina is going to talk about extracting user locations from mobile instant messengers. Thank you, Katharina. You can start.
Thank you for the introduction, and thanks for having me. So, exactly, this talk is going to be about learning someone's location just from sending them a couple of messages. So, the context of this whole attack that we're going to look at is that let's just assume we have a person waking up, realizing it's such a nice day, and they're supposed to work. And they think about their office setup and the boring desk and the boring computer, and they look outside the window and say, all right, the sun is shining. Even though I work from home, it's so boring. I want to go swimming instead. So they're sitting at home, right in the dilemma of going to work like they're supposed to, or going to the beach instead, and wondering if anybody would notice because you work from home. Your boss can't see that. What should happen? What could possibly go wrong? So in our story, our person decides, okay, let's just sneak off. Let's go to the beach, enjoy the sunshine, drink a glass of juice, stare at the sea, have a nice and relaxing day. So they start taking off. And instead of going to the desk in the home office and sitting there in front of the computer the whole day, our hero just takes a detour, goes to the beach, and enjoys the day, enjoys the sunshine. The problem now is, while relaxing, the phone goes ding, and they receive a message coming in from Eve. You're not at work. And now our hero is a bit concerned, because how would anybody know that? How would they be able to realize that they're not in the home office working, because nobody can look inside? Nobody would be able to see that. But still, someone caught our hero. So what's happening here? We have one person, Eve, who's the attacker, sending a message to another person, and they're very interested about the location of that person. So I just sent a message, and in return, they received the location of the victim. This is basically what this talk is going to be about, and what the background of this attack is. You send a message to a person, and then you can determine the location of that person. So that's a setting that we're going to start with. Eve sends a message and learns the location. And that's quite a bad setting, because I would assume, I can't see the audience right now, but I would assume that everyone might be carrying a smartphone, and that everyone might have sent a couple of messages already today, and maybe received a couple of messages. And that's what you need for this attack. You send a message, you analyze a bit of data, and then you get the location. And that's kind of privacy sensitive, because location is important information. So this is all part of a paper that's called Hope of Delivery, Extracting User Locations from Mobile Instant Messengers. We published that at NDSS in 23. And it was, and you will see that later in the measurements, it was a joint project at different locations. So in Germany, the Netherlands, and in Abu Dhabi. And what we will focus on, what's very important here, is we want to extract user locations. So you reveal a location without any consent. It says mobile instant messenger. So wherever you carry your phone, you carry your device, wherever you take it, that's where you might be localized. And it's using instant messengers, which is like a group of apps where it's very likely that you're going to use them. So you already use them on a daily basis, and the adversary can exploit these mobile apps. So this is our setting. This is the context that we will work with. Big question, how is this possible? And we won't go into detail with everything. That might be a bit too much and be a bit too boring, but I'll give you the general concept of how this works. So there's a fundamental principle that we can make use of here. We look at information from transmission times, because time, speed, and distance are related. That's a very obvious relation. When you go somewhere by car, by train, or whatever, then that vehicle travels at a certain speed, and this allows you to travel somewhere in a certain time, and you manage to travel a certain distance. That's how they're all related. And we can make use of that. We can learn time and speed from transmitting information, so we can get the distance. And getting the distance means that we can get information about locations. And that's a very simple concept in general. So when you are somewhere and you do a timing measurement, you send out a probe to that point, you wait for the response, you can measure how long that takes. So let's just say it's 20 milliseconds to send something back and receiving the response. Then you can take this very simple equation, speed times time equals distance, and you already got the time. And we can just assume a speed. We can just say it's when we transmit information on the internet, it travels at the speed of light. Disclaimer, it does not. The internet is slower, but this is pretty much the upper bound that we can get right now with our technology. The highest speed that we could achieve transmitting information is the speed of light. So we measure 20 milliseconds back and forth. So the distance, let's just say it's 10 milliseconds for one direction. 10 milliseconds times the speed of light equals to roughly 3,000 kilometers. So if you transmit information, then the maximum that it can travel in that time is 3K. That's it. And this allows you to draw a circle around your location where you're currently in, with a radius of 3,000 kilometers. And that is your search space. That's a rather big search space right now for our example, but it already gives you the idea of what we will be doing. You measure timings, you assume a certain speed, and then you get an area where you can search. And by doing this a little bit smarter than this, you will be able to localize users. So this is the fundamental concept that we're going to apply in this attack. That's what we're going to make use of. How does this help us? You get a plausible search space. So this is Europe. I just put the point somewhere. I just drew a circle around that. Just an example. It's a rather big search space, but if you have multiple measurements and if you can make it smaller and if you have more information, then you get quite good information and a lot of hints and pointers that help you to narrow down the location of a target. And that's what we're doing in this attack. So, how does Eve localize our hero in the story? That's the main question, and we will approach this now from a more technical perspective. We need to find out how things are connected. How can we measure timings? How can we derive distances? How does this help us? And what can we accomplish with this? So we get a task list. First item is we want to send a message to the target. This is something that you can do with your phone. If you have someone in your address book that you can send a message to, this is a person that you would be able to attack with this whole concept. Then Eve needs to analyze the timings, because just sending a message doesn't give you enough information. You have to analyze the timings. And then you can check the plausibility of a location. In our example, our hero was supposed to be at home working at the desk, but they wandered off to the beach, which is a totally different location. because their home office is not located at the beach. And this is what Eve can do. She can check the plausibility of the location she gets from the analysis. And we'll just go through these tasks now step by step and see how this can be accomplished. And we'll begin with the part where you send a message to the target. And the big question is, what can we learn from that? So when you send a message using one of these instant messengers, what you most likely will get is you have the sender, which is you with your phone. You have the receiver on the other end, that's the person that you target, but you will have at least one intermediate server. So just following the example of WhatsApp, if you send out a message, there will be a first check sign that you get when the message arrives at the server. So when you send out a message and you see this check mark right to your message, you know it now arrived at the server. And then the server forwards the message to the receiver. And then on the way back, you get a notification that the message now arrived at the receiver. So if you have two check marks, what you learn from that is your message arrived at the sender and at the receiver, and the acknowledgement of that took all the way back to you. So one check mark gives you the back and forth to the server. Two check marks give you the back and forth from sender, server, receiver, server, sender. So the whole way back. And we can use this information. So first point, messengers use intermediate servers. This gives you these check marks and we can make use of that. First part is we know how long it takes until the message arrives at the server. So this is the time between sender and server. And we can get the time it takes from the sender, from the server to the recipient and back. This is the double check mark. And deriving these pieces of information from the transmission, from the message that you send, this gives us the information that we need for the attack. And for this, what's very important, we know that the server is the intermediate node. We are interested in the destination, so the recipient. So we need to learn where the server locations are, because if you just take one of the check marks, you don't get the recipient. That doesn't help us. And if you take the two check marks, that's very good because the message arrived at the recipient. But we still have this hop in the middle of the intermediate server. And that gives us a lot of noise if we would just take this timing from the double check mark. But if we know the server location, that's one more piece of information that we can use. And that helps us a lot with the localization. So let's see where the servers are located. We looked at different prominent instant messenger apps in our paper. And when you start looking for server infrastructure, you get no public information for Signal. You get some hints that Threema has servers in the Zurich area. And for WhatsApp, it's pretty much clear that they will use the infrastructure of Meta. So the whole server infrastructure of Meta might also be used for WhatsApp, or at least parts of that. So what can we do? We can collect empirical information about the servers to learn more about the server infrastructure. So how many are there? Where are they located? How are they picked? Is there any strategy on how to pick the server if there are multiple servers in the connection? So this is one big preliminary step that we have to accomplish before we can conduct the attack. And how do we do that? Well, we can't just ask. It's information that they're not likely to share, but we can just measure that. Just take a bunch of phones. You write a script, and with the script you send a lot of messages to other phones. And if you record the traffic, what you get is a long list of IP addresses. So if you send out a message, the destination IP is the server, not the recipient, because the server is the intermediate hop. So whenever you send out a couple of messages and you record the traces, you will get the destination IPs of the intermediate servers. And if you send messages from different locations, then you get additional information telling you that there might be multiple servers, they might be in different locations, they might be picked according to your location, so maybe trying to be as close to you as possible. And by using like different measurement times and a lot of repetitions, you get data that helps you understand the infrastructure a bit more. So we did that. We took a couple of phones, we sent out a lot of messages using scripts, and then we received a very extensive IP data set that we could analyze to understand the server infrastructure. And what you can do with IP addresses, I mean, they're not very interesting just as the plain numbers, but what you can do is make reverse DNS lookups and extend the IP information with more stuff. Whatever you can get your hands on, whatever is useful for understanding the infrastructure. So the example that we look at right now is just asking for the DNS records of an IP address that we saw in our measurements. You get the host name for an IP address. This whole thing only works if there's a record existing and if it's properly configured, but we will just assume that that's the case. And what you see here, underlined in red, is the host name of one of the meta servers that is used for WhatsApp. So it's got still Facebook in the name, and what you see is a rather long string indicating a couple of different pieces of information. So for WhatsApp was very interesting because there are a lot of servers worldwide, and they use these IATA location codes. So when you look at the host names that you get from the IP addresses, then you get these short codes in red that you see here, and they already indicate a location. So LAX is Los Angeles, LHR is London, CDG is Paris, and so on. So just from the IP addresses and the host names, you get locations that definitely point to a place in the world and where you can locate the server and the according IP address. This is something that's only possible for WhatsApp and the meta infrastructure. It helps us to verify assumptions about locations because IP addresses and geo IP information is not always reliable. But these are very good pointers for us to get the locations. And after doing this, sending a lot of messages, collecting a lot of information, this is what you get. So all the green dots that you see, that is infrastructure from WhatsApp. You see some dots in the ocean, which is a very good indicator that empirical data is not always perfect, but the majority of these points is reasonable and can be used for a data set. You also see that there are not so many signal and Threema servers. So Threema, we assumed them in the Zurich area, and this is still correct. And then the signal server is on the East Coast in the US. And this is already an interesting picture because you see that WhatsApp has a lot of infrastructure. It is the biggest messenger of the three. And it also means that the load is well distributed among these servers, whereas if you send a signal message, it will travel to the East Coast and it will travel back. So there might be longer delays here. And for WhatsApp, you have less noise of these long detours. And this is now information that we can use in our model and that we can use for the localization. Because we send a message, we learn the arrival time at the server, we know the IP address of the server, and we now know the server locations. So we can estimate which server was used, and we already have, it's like a longer equation, and we can put in a couple of numbers here, and we can remove a couple of the question marks in the equation. So this helps us identifying where the receiver is located, because the first part of the connection we already kind of check out. So this also checks the first item on our task list. We send out messages using one of these popular instant messengers. We get delivery and receiver notifications And we can time those, we can measure those. Like if we look at the transmissions, we record them, we analyze them, we see when we receive one of these check marks or the double check mark. And we can know the server infrastructure because we have empirical data about that. And it is not 100% correct, but the majority of server locations are. And we can rely on that and use that for the next following steps. So next step would be analyzing the timing that we get, because we're not so much interested in the server, but in the destination. So there are a couple of challenges here. Whenever you do timing measurements on the internet, you have to expect that they vary a lot. There's a lot of noise in the transmissions because you have dynamic routing. The route that information takes is not always the same. You have congestion, depending on the time of the day, it varies a lot what performance you can get. The receiver might not connect to the same server as you do. So there's more noise. There's one more hop that you don't know about because it's behind the server and you don't see any IP address. That adds noise as well. And locations can be very easy or very hard to guess. We'll see why that is the case in a couple of minutes, but as a short notice on this. What Eve can do is check whether the person is in a certain location. And if locations are very close to each other, it's very difficult to be sure about the exact location. Whereas when you have to distinguish between two different continents, it gets easier. So we analyze the timing now, and we have to send a lot of messages again, back and forth. So what we can do for our experiments, and what is also part of the attack, we prepare a labeled data set that we train on. For that, we send repeated messages. We have the same setup again. We have phones in different locations, and we know these locations. Those are the senders, and we have receivers in different locations. We know them again, so we have a labeled data set. We have a ground truth. And we can test different messengers. So we just keep on sending messages, and we use the different instant messengers on the phone. And all of this results in a classification problem because we have receiver locations, for example, countries. Those are the classes, and we want to find out, based on the timing, where what class the receiver is, what location the receiver has. So by sending out all these messages, we generate a huge labeled data set. And we can now use this data set to check the plausibility of a location, to conduct this final step of the attack. And because so far it was an interesting attack concept, now we get to the scientific parts again. It's not that we run around and attack people. We have to define different scenarios, and we have to define different goals. We have to analyze the performance to see how reliable the attack is. So there are 4 different things that we are interested in, that we covered in our paper. First one is, what is the receiver's country? So there's a list of potential target countries, and we want to find out which one it is. So it's not an arbitrary guess of at what geolocation is our target anywhere in the world. It's about finding out if they're in one of these known countries. Then it's a binary question. Are they within a country? Did the person of our story, did they leave the country to go to a beach in a different one? Are they still here? Where are they exactly? This is very challenging. So it's not so much about a country in a very large search space. It's more about, is someone in the ID building on the campus? Are they in the MC building? Are they in the Audimax? Are they in the gym? This is very difficult because it's all the same city. And finally, what connection do they use? Because it can make a huge difference to be on a Wi-Fi connection or to use a cellular connection. So these are the 4 questions that we ask, and we try to apply our classifier to find this out based on timing information. So in our experiments, we send a little more than 240,000 messages in different combinations, different countries, different locations, different devices, different apps. And we use this data set to find out, or to give a first indication whether the attack would work. So what we do, like you would do in any scientific work, you have your large data set, you split it up a couple of times in a big training set that you can use to analyze and prepare, and a small test set that you then use to analyze what performance do you get. And then for each sample, we get the probability that it belongs to one of the classes that we're looking for. We can compare the results with our ground truth, so we know where we did a correct guess or a wrong guess, and we use a neural network for the classification. And I won't go into detail with all the results that we had. I'll just give you an example of identifying the receiver country. So this was the first of the 4 questions that I listed. And what you see here is basically a confusion matrix showing whether a guess was made for the right destination. So on the diagonal line in the middle, you see correct combinations, and you want to have a high number there. And every other combination would be a wrong guess. And what you see here is that for the majority of guesses that we did with the classifier, it was possible to find the right match for the destination country. So you see the overall results for the different messengers on the right, and it ranges between 74 and 84% of correct guesses for the different messengers. Which leads to the conclusion, yeah, in general, it kind of works. So for a task list, this means we can send out a message, we can analyze the timing, we have empirical information that we can use that helps us, and we can use this to check the plausibility of a location. Like we have our classification challenge, and it seems that we're successful with that challenge. So, conclusion, we can guess the location of the receiver without their consent. Big question is, what's the catch? And there are quite some limitations to this. First one is you have to obtain a training set, and that can be very annoying for the target because it basically means sending messages over and over again. So if you're somewhere and you keep on receiving messages over and over again without any useful content, and it's very conspicuous, that's an indication that something is going on that's not supposed to go on. I don't think that people run around and actually implement this attack, but this would be a very good indicator. So first limitation is obtaining a training set might be very conspicuous, especially when you just keep on sending repeated messages to a target. Second limitation is the attacker model. It is a very nice and simple and smart attacker model, but it is not a very common one. You can conduct this attack when you know the victim, and you need the phone number or the contact of the instant messenger, and you need to know the locations that they're usually in. So if Eve knows that our hero is either at home office or at the beach, it's rather simple to find one of these classes, just based on the timing, especially if home office and beach are very far from each other. But if there are new locations that Eve doesn't know about, it might be very difficult to find out where exactly the user is located, because you don't know that location. You can't really narrow it down just from this attack. So the attacker model has limitations. It is very simple because you only have to send messages, and instant messengers are everywhere. But the attacker has to know the victim, and you cannot make an arbitrary guess on any location. You can just verify known locations, which is, it's still nice, I could send a message to someone, like to one of my students, and verify whether they are in the office or not. But it's not that I can just take an arbitrary person and say, you are located right in this, at this latitude and longitude. And then finally, disabling these delivery notifications would remove the source of information that you need for the attack. Not all apps allow that, but it would be a very simple fix and like a defense against that attack. And this brings me to the conclusion of my talk. So what should you take home? First important aspect is that transmission times contain information that points to locations. And that is not a concept that is limited to this attack and messengers. It is a concept that applies to everything that has a transmission speed and a time that you can measure, and that then relates to a distance. That's a concept that you can apply everywhere. Then you can implement an attack that's based on timing information, and you can augment this whole approach with empirical information, like the infrastructure of servers. And then eventually you can send messages to guess the target's location. And on paper, this is a successful attack. It does work. There are some limitations. And you always have to keep in mind that the attacker model is rather specific about the requirements. And this brings me to the end of my talk, and I'm happy to answer questions.
Okay, let's start with questions in the room.
Hey, thank you for your talk. So the attack involves only one instant message, right? Did you try to, for example, in WhatsApp that has multiple servers all around Europe, did you try to send 3 or 4 messages each to a different server and try to triangulate and find more information about the user, about the victim?
That's definitely something that you can do. You would need multiple devices in multiple locations for that. And the problem is a bit that you can only influence your server. So the destination will connect to their own server. So it's not like in a classical setting where you can really just have multiple references and then narrow down the search space of the destination, because you always have these intermediate servers. It would definitely help, but it is not as simple and as straightforward as in GPS.
Yes, thank you. Any other questions? Yes.
Hi. So if I want to defeat this attack using Signal, can I just draw a circle on a map around the east coast of the US and only go on vacation on the circumference of that circle?
No. No, because it would, like, if my location, if I'm the adversary, my location is static, then, and the server is static as well, then you moving around will introduce differences in the timing. I mean, if you stay very close to the server, I won't be able to localize you. But otherwise, it should be possible to still localize us, to still narrow down where you're supposed to be.
Hey, Katharina, thanks for your talk. I was wondering, in your measurement, did you assume that whenever people are at home, they're going through the Wi-Fi network, or do you also consider that they might change to like mobile network if they, like, let's say, move to another place in like at home?
So we did experiments with Wi-Fi and cellular connection because the infrastructures are so different, and in a cellular connection, you have more noise, more overhead, because you have to route through the core network and then the internet. We didn't have a scenario where we would have a user that changes in the middle of the experiment or something like that. But we do have experiments covering distinguishing Wi-Fi and cellular, and that works as well. So we are also able to distinguish what kind of connection you're on.
Hello, Katharina. Hello, Katharina. This is Savio from TUI. A question. Can this same technique be used, for example, by the WhatsApp provider or any other provider to localize users?
Yes, because the delivery notifications, well, I'm not sure if you would need all this overhead of this attack. What the WhatsApp server sees is the destination IP of the delivery notification that's being sent out. And they see the connecting IP address as well. So they pretty much already have IP information about your location. And it's like IP information is not always perfect. So you could try to improve what you get out of that, but in most of the cases already reveals your location. I mean, if you go on one of these web pages where you check what your IP address is, you always get location information as well. And as soon as you have an IP address, you have location information.
Okay, thanks.
Thank you. I see some more questions. Yes. Yeah.
Hi, thank you very much for your talk. I was wondering, modern chat apps like the ones you've covered typically provide some way to, set up voice calls, and this typically happens using a protocol called WebRTC, which sets up peer-to-peer connections. It's obviously a well-known attack vector that this allows you to identify the IP address of the other party. And so these services offer a proxy that allows you to hide the IP address for the other party. I was wondering, have you considered doing the same timing attack for voice calls with this proxy server in the middle?
We have not. And I would assume that is a very similar setting. The question is what piece of information would we use for the timings? Because what we use right now is the delivery notifications, and they help us to localize the server and then already have certainty about that part of the connection. So you would still need information about the proxies that are being used. But I assume that because you have a similar source of information, a similar type of attack would be feasible.
Yeah, so the reason why I'm asking is in this situation, you have a bidirectional audio stream. And so you could maybe use this as a continuous stream of timing measurements.
Yes, you would definitely have a lot more information to use for the attack. It's like repeated messages, and more data is always good for timing measurements on the internet because of the noise that you get.
Okay, thank you.
Thank you. We have another question.
Have you also considered the scenario where the victim of this attack is using roaming on cellular network? That usually involves that the traffic is relayed then back to the home country. This will make this kind of attack an effect, right?
So we would have a setting with a cellular connection for at least the victim using roaming. Then it depends on the roaming setting, because you can have a local breakout or what was the other one called? So there are two different options where you have the roaming partner connect to the home network, or having I think it would be much more challenging because you have a lot more hops in between. But the roaming setting itself is also something rather static that the adversary would be able to learn. It's a bit like the server infrastructure of the messengers. You can also learn the infrastructure of mobile operators because it's very similar, and I think they have way less servers than WhatsApp uses. So yes, with this implementation, it would be very challenging, but it is static information that the adversary could also train on.
Okay, thank you.
Okay, we have time for one more question, and then the
That was
rest.
someone else.
Okay.
I'm sorry.
No problem.
I have to be fair.
Hi, thank you for your talk. When you presented the accuracy results for the guesses at the end, out of your 3 apps, I noticed that while you have WhatsApp, which has, as you said, a lot of different servers, Signal and the third one, whose name escapes me at the moment, seem to have a big gap in their accuracies, even though, unless I understood wrong, they both use central servers, one in Zurich for the unnamed one and one in the East Coast for Signal. Have you explored why there's such a discrepancy between the two? Because it seems, at least to me, maybe naively, that having central servers would make them behave similarly, or maybe one of them has more noise. Have you explored why there's such a big difference?
We didn't explore that. My assumption is that the Threema server in the near Zurich is much closer to the reference points where we conducted our measurements. So we have very strange, the locations where we conducted measurements are pretty much biased by where we do research. So they're in Germany, Netherlands, Greece, and in Abu Dhabi, which is all pretty far away from the East Coast, but around the Zurich area. So we have less noise. And my assumption would be that this influenced our results to an extent where you see this difference between, it's I think not so much about Signal and Threema, it's more about East Coast and Europe.
Okay, thank you very much, Katharina. We have to move on. For the rest of the questions, maybe you can put them online. Let's thank Katharina again, please.